Heinrich Hertz in 1887 is doing experiments with electromagnetic radiation. That's what he did, right? He's got a unit named after him for frequency, and that comes from his experiments with electromagnetic radiation. He was the first guy to experimentally verify Maxwell's theory of electromagnetic radiation using that spark gap apparatus that we talked about on the second day of this unit. He's performing more experiments with EMR in 1887, and when he does that, he discovers by accident an effect that will sometimes happen called the photoelectric effect. It says, as we talked about on Friday, that when light strikes a piece of metal, sometimes an electron will be ejected. Not always, but sometimes an electron will be ejected. Now, Hertz reasoned that if an electron was ejected, it was because the electron received enough energy from the light to be released. Okay, and that part of his reasoning was correct. In order to cause an electron to be ejected, you need energy. If the electron wasn't ejected, then Hertz reasoned that it was because the electron wasn't receiving enough energy. Good, good, it's not. Okay, that part of his explanation is still correct. But he reasoned that to get more energy to the electron, you needed more light. So in other words, if a dim light wasn't causing electrons to be ejected, we needed a bright light. But as we saw with our little demonstration on Friday, bright light isn't going to cause anything to happen if dim light of the same kind doesn't cause anything to happen. There is a certain minimum frequency necessary to eject an electron that we call the threshold frequency. If the light is below that frequency, nothing happens no matter what. It doesn't matter how dim the light is. It doesn't matter how bright the light is. If you're below the minimum frequency, nothing will happen. So, people prior to Einstein in 1905 observed that certain kinds of light would cause it, certain kinds of light wouldn't cause it. It had nothing to do with the intensity of the light, but rather the type of light, but nobody could figure out why. This is when we enter Einstein in 1905 with, we talked about his miracle year, right? In 1905 with his photon theory that we addressed on Thursday. Photon theory says that light exists as a particle, and the energy of that particle is equal to h times f. It's also equal to hc over lambda. So in other words, the energy of the light, according to Einstein, isn't the intensity of the light. The energy of the light is related to the frequency of the light, the type of the light. This explains why certain kinds of light would cause electrons to be ejected and certain kinds wouldn't. If you've got a type of light that doesn't cause it, more of it doesn't do anything. But a different frequency, a higher frequency, does, because it's frequency that changes the energy of the light. Hertz was right. You need more energy to cause the electrons to be ejected. But you don't get it from intensity, you get it from frequency. Okay, that's Einstein's photon theory, and that correctly explained the observations that were made for the photoelectric effect. Therefore, Einstein's photon theory was accepted at that point. Okay, prior to Einstein, we call it classical theory. Okay, it's old style physics. It's physics before the introduction of what we call sometimes quantum theory. Okay? As soon as we enter Einstein, that's quantum theory. So Hertz's explanation, classical theory. Einstein's explanation, quantum theory. All right, threshold frequency. We talked about this a little bit on Friday, given by the symbol F0. F0. Usually when you have a zero subscript, it means like a minimum value. Threshold frequency means the minimum frequency of a photon necessary to eject an electron. If you have a photon above that frequency, a photon will cause an electron. In fact, if you have 4 photons above that frequency, it's going to cause 4 electrons to be ejected. Or 6 million photons above that frequency, then 6 million electrons will be ejected. It's a 1-to-1 ratio if you're above the threshold frequency. If you're below the threshold frequency, it doesn't matter how many photons you got, you're not going to get an electron to be ejected. The work function, given by the symbol capital W, real closely related to the threshold frequency. If we have energy of a photon, according to Einstein, equal to h times f, or hc over lambda, then the minimum energy would be equal to h times the minimum frequency, which is the threshold frequency. It would also be equal to hc over the threshold wavelength. But the threshold wavelength isn't the minimum wavelength like frequency is. Rather, it's the maximum, right? And why is it the maximum? Good, because the frequency and the wavelength are inversely related to each other. As one goes up, the other goes down. If you look at the equation, C is equal to F times lambda. If this stays the same, okay, as frequency goes up, wavelength goes down. Okay, if one's going to be a min, then one's going to be a max. So you could solve for, using the work function equation, the minimum frequency, okay, anything below that, nothing happens, or the max wavelength, anything above that, nothing happens. This is more of what we've already said here, right, guys? So photons below the threshold frequency, and therefore below the work function, because if you're below a certain frequency, then you're going to be therefore below a certain energy. If you're below the threshold frequency, below the work function, nothing's going to happen no matter what. A single photon will cause nothing. 1,000 photons will cause nothing. But if you're above the threshold frequency, 1 photon will cause 1 electron. 1,000 photons will cause 1,000 electrons. What if you're way above the threshold frequency? Not just barely above. Okay, we got a photon that's barely above. Okay, that photon caused an electron. 1,000 photons barely above. Oh, it caused 1,000 electrons to be ejected. What if you got a photon that's way above the threshold frequency? Roger?
You got 1 electron that is way more.
Good. You're going to have a 1-to-1 ratio still. 1 photon, 1 electron, 1,000 photons, 1,000 electrons. But the energy of those electrons is going to be greater. So you're going to have more energetic, faster moving electrons as a result of the more energetic photons. Look, if you got high energy photons, then the energy's got to go somewhere. It doesn't go into causing more electrons, so it's got to go somewhere. It's got to give the energy, the electrons that are released, more energy. Okay? More energetic, faster moving. Because in the end, the electrons that are released, the energy that they have is kinetic energy, right? If they've got more energy, then it's got to be because they're moving faster. A couple more terms. We talked about threshold frequency. I'm going to put these at the top. Threshold frequency, work function. Okay, we've already addressed those. Another one, stopping potential. Now, this one might seem a little bit odd right now, but just listen carefully for a second and bear with me. Stopping potential is a potential difference, okay, a voltage, okay, a potential or potential difference required to stop an electron that's already been ejected. It doesn't really have anything to do with the photoelectric effect per se, because the electron's already been ejected. If an electron's been ejected, we can stop that electron dead in its tracks by applying a potential difference. It's kind of like you got a go-kart or a bike rolling along the ground there, and it starts rolling up a hill. The hill can stop the bike or the go-kart. The hill can stop the go-kart, right? The kinetic energy of the go-kart that it had at the bottom of the hill will be converted to potential, and you can make that go-kart stop. You can do the same thing with an electron, convert the kinetic energy of the electron into potential energy, but this time it would not be gravitational potential, it would be electric potential energy, Q times V. So it's kind of like what we did back in Unit 2, when a car is going up a hill, okay, when a charged particle is slowing down, it's like a car going up the hill, and it's kinetic energy conversion to potential energy. Now, why would we want to do that? What's the purpose of doing that? Okay, the photoelectric effect has already taken place. The electron's already been ejected. Why would we want to stop it? Well, we might want to find some properties of this metal, like the threshold frequency. Maybe we're designing a new solar cell, okay, in order to power a calculator or in order to power a house. Okay, we want to design this new solar cell, and we need to know what the threshold frequency of the metal is that we're trying to use. Maybe we're just doing experiments where we want to find threshold frequency of different metals so that somebody else maybe can build solar cells with the best metal given certain conditions. If we want to find the threshold frequency, then we can do an experiment by stopping the electron dead in its tracks and then working backwards to find the threshold frequency. I'll show you how you do that here in just a few minutes. Bottom line is, sometimes we would want to do that. Okay, we'd want to stop that electron once it's been ejected. So I'm going to say stopping potential, symbol is V stop, and it is the potential difference required to stop an already ejected. So we're not stopping it from being ejected. We're not stopping the photoelectric effect from happening. It's already happened. We're stopping the electron that's already been ejected. We're literally making it come to a stop. It was moving, now it isn't. The potential difference required to stop an already ejected, we'll call it photoelectron. What do you think I mean by that, photoelectron? Sometimes we see that term. What's a photoelectron? Same as any other electron, right? Except this one's been ejected as a result of the photoelectric effect. So it's the electron that's been ejected. Now, I alluded to this a second ago. It's like you're stopping an electron that's moving. You're slowing down. You're stopping. You're causing a change in speed of a charged particle. That's a conservation of energy problem, right? That's like a car going up a hill. The car at the bottom of the hill would have kinetic energy. As it goes up the hill and gets converted and comes to a stop, that would be converted to potential energy. What we're going to say is this, guys. We're going to say the kinetic energy, or at least the maximum kinetic energy of the electron that's been ejected. We say maximum because we don't know exactly how much energy it has when it's been ejected. We can only predict the maximum amount, assuming the energy conversion is 100% efficient. The maximum kinetic energy that it would have when it's been ejected is 1 FmV squared. 1 FmV max squared, we'll say. But that gets converted to potential as we stop it. So we're going to say that we convert kinetic energy into potential energy, QV stop. EK is equal to 1 FmV max squared equals QV stop. So now we got a couple equations. This one that we just wrote down, and that one we wrote down on the page before this for a work function. I'm going to give you one more now. And this is probably the most commonly used one for the photoelectric effect. Unfortunately, it's the one that's not on your data sheet. Why it's not on your data sheet, I'm not sure exactly, because it used to be, but then they took it off. It is really just another statement of the law of conservation of energy. Maybe that's why. Maybe that's why they don't give it to you, because in the end, they don't give you 1 FmV squared equals QV, or mgh equals 1 FmV squared. That's conservation of energy, and you figure that out. This is too, so maybe they just expect you to figure this one out as well. Now, in this whole process of the photoelectric effect, we start off with a certain kind of energy. What kind of energy do we start off with? What is it that has the energy at the beginning of the problem, before an electron's been ejected? You picture this. A photon strikes a metal, an electron is ejected. What has the energy at the beginning of this problem, right? The photon. Good. So we're going to say the initial energy is the energy of the photon, which is hf. Or we could also say hc over lambda. So the energy that we start with, h times f. What has the energy at the end of the problem, after the electron's been released? Yep, the electron, good. And what kind of energy does the electron have when it's released, Rucker? Good, it's kinetic energy. So we're going to say it's 1/2 mv squared. We're going to say 1/2 mv max squared because we can't predict the exact kinetic energy it has, just the maximum kinetic energy it has. So EI equals EF, right? The energy that we start with equals the energy that we end up with. except that it's not true. The energy that we start with isn't the energy that we end up with because you lose energy in the process of emitting an electron. The energy that you lose in the process of ejecting the electron is the work function. So we'll say the energy that we start with equals whatever we end up with plus whatever we used up in the process. We start with 100 joules, we end up with 80 joules, well, we used up 20 joules, so 80 plus 20, what we end up with plus what we used up in the process of ejecting the electron is equal to 100 joules, which is what we started with. These two in slightly different forms are on your data sheet. And when I say slightly different forms, it's things like, it says on your data sheet EK is equal to QV stop. It says somewhere else on your data sheet EK is equal to 1 FMV squared. You got to kind of put those together, okay, but it's there. Okay, this one is not there. This one you've got to build from scratch. But the good news is, if you remember that it's the law of conservation of energy, you can figure that out, right? The energy of the photon equals the energy of the electron plus the energy that I used up in the process. Let's try a problem there. Page 716, it says blue light shines on a metal surface in figure 1413. It doesn't matter about the diagram there. It causes the photoemission of electrons. What does that word mean, the photoemission of electrons? We haven't said that yet, hey? We haven't used that word. What does that mean, the photoemission of electrons, Maddie? Yeah, the ejection of electrons, right? If a stopping potential of 2.6 volts is required to completely prevent the electrons from reaching the collector, what does that mean? The stopping potential. We talked about a stopping potential. If a stopping potential of 2.6 volts is required to completely prevent electrons from reaching the collector. To completely prevent electrons from reaching the collector. What's another shorter way of saying the same thing as they just said there? John? Yeah, to stop them. If you want to completely prevent them from reaching the collector, you've stopped them. So this is our stopping voltage, right? Or our stopping potential. We want to find the maximum kinetic energy of the electrons. We want to find EK max. And we want to do it in joules and electron volts. All right. Let's go back to the last page and take a look at what equations we have that we might be able to use to solve for EK max. This equation is for EK max. This equation has EK max in it as well. Which one do you want to use? Probably the first one, right? Probably EK is equal to QV stop. Do we have the charge? We're talking about, Jazzy, we're talking about what? What has been ejected here? An electron. Do we know the charge of an electron? Sure, it's the same as any other electron, right? Just because we sometimes call it a photoelectron doesn't mean it's a different thing than the electrons that we've been dealing with since March. The charge of an electron is 1.6 times 10 to the minus 19 coulombs, and the stopping potential is 2.6 volts. What does that work out to be, Cole? 4.16 times 10 to the minus 19, and that's going to be what units? What units? Yeah, what units is it? No. Joules. It's going to be in joules because we used our standard units, right? Coulombs and volts. Those are our normal units. And when we use our normal units, we're going to get normal units or standard units out of it. Now, we should technically round that, Cole, to 4.2, right? 2 digits, right? Okay, we've dealt with problems involving photon theory where we've had joules or electron volts. If you're using standard units, all standard units, then you're going to get standard units out of it. If you're using coulombs and volts, you're going to get joules out of it. Now let's convert that to electron volts. Let's say 1 electron volt over 1.6 times 10 to the minus 19 joules equals x electron volts over 4.16 times 10 to the minus 19 joules. We do the math there, it works out to be 2.6 electron volts. Why is it the same number as volts here? Is it always going to be the same number as volts? When you're dealing with an electron, yes. If we're dealing with something like an alpha particle, then no, right? Because the charge is different. Now, you're not going to be dealing with an alpha particle in the photoelectric effect, right? It's always going to be an electron. So it will always be the same number. Okay, 2.6 electron volts, 4.2 times 10 to the minus 19 joules. Before you start working on the couple questions that go along with this, I want to draw your attention to something. We ended up solving for the kinetic energy here in joules, right? Remember I told you that when we did photon theory that Planck's constant has two values? 6.63 times 10 to the minus 34 joule seconds. 4.14 times 10 to the minus 15 electron volt seconds. And I said, usually you can use whichever value you want, whichever one's convenient. But there are exceptions to that. I told you I'd tell you what those exceptions were when we got to it. Here's the exception. You can use either one for this, for this, for this, for this, for this, even for EK. You can use electron volts. But as soon as you introduce either of these two equations into the mix, 1F mv squared or QV stop, you must use joules. For anything else, use whatever you want, whatever's convenient. Again, even for EK, right? Even if I replace this 1F mv squared with EK max, I could use electron volts. That'd be fine. But if I put in 1F mv squared or I put in QV stop, then I've got to use joules. If that confuses you at all, then what should you do? Always use joules, because joules always works. It just sometimes ends up being a little bit more work, but it always works. So if you're confused by what I just said, then just go joules always. All right? Take a look at these three questions, please, over the next couple minutes. Okay, we got no issues with those three questions. Let's try another one on 718. It says, experiments show that the work function for cesium metal is 2.1 electron volts. Determine the threshold frequency and the threshold wavelength for photons capable of producing the photoemission for cesium. So here's the work function, W. It's in electron volts, remember. I'm going to circle that, even though I don't necessarily have to convert that. I may be able to leave that in electron volts. I'm going to circle it because I might have to convert it. I might not have to convert it. I just want to remember that it's non-standard units in case I have to convert it later on. What's the threshold frequency and wavelength for photons capable of producing the emission from cesium? In other words, what's the minimum frequency and the maximum wavelength that is required to eject these electrons? We're looking for F0. We're looking for lambda max. Well, if we go back to that page that has my equations on it, we've got basically three equations with various parts to them. What do we want to use? Want to find F0, want to find lambda max, got the work function. What do you want to try? Yep. Good, good. Let's say W is equal to HF0 first to find the threshold frequency. Now, we've got the work function in electron volts. Can I keep it there? Yes, I can. Why? Why do I not have to convert it to joules? Well, there's only two situations where I have to convert it to joules. What are those two situations? Ready? Right, when it's 1F mv squared or QV stop. I don't see 1F mv squared or QV stop in here, so I can use electron volts if I want. Hey, if you want to convert that to joules and then go with joules the whole way, then be my guest. You'll get the same answer. But you can save yourself a step here and use the electron volts. But remember, if I'm using 2.1 electron volts, what value for Planck's constant am I going to use? Good. 4.14 times 10 to the negative 15 electron volt seconds. Okay, you convert that to joules and then use 6.63. Guess what? You're going to get the exact same frequency, whatever that is. 5.07 times 10 to the 14. Okay, thank you. And that's going to be, hey, what if I asked you what kind of EMR that was? What would it be? Infrared, visible light, ultraviolet? Forget about the color. This is going to be visible light, right? Because it's in that range of 4 to 7.5 times 10 to the 14. Okay, that wasn't asked here, but if it was, you know it was visible light. All right, you want to find the wavelength now. I see a couple options for finding the wavelength. What's one of them? Brad told me at the beginning that I could use the equation W is equal to HC over lambda max. Does that work? Sure it does. Lambda max is equal to HC over the work function. Do the same thing here, guys. 6.63 value? Well, only if you convert the work function to joules. Okay, if I'm using electron volts, then I'm going to use 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by the work function of 2.10 electron volts. I don't know what I get there. Something times 10 to the minus 7. 5.91 times 10 to the minus 7. Okay, thank you. 5.91 times 10 to the minus 7 meters. Good. Okay, you use joules. That's going to work out as well, as long as you convert this to joules. What's the other option? Anybody see a slightly shorter way of doing it? Not much. It's not much of a time savings at all, but yep. Yeah. B is equal to F lambda, or C is equal to F lambda. I just solve for frequency, right? We know what C is, 3 times 10 to the 8. I just solve for frequency. I could turn around and solve for lambda here. It's a little bit shorter because it has 3 variables in the equation instead of 4, but not much of a difference there. Okay, whatever works best for you. All right, let's try these 2 questions and then go along with those. All right, then if those 2 questions are good, let's try one more example question. This one is on page 719. This one says using table 14.1, so we're going to need some information from this table, information that probably won't appear on a test or a diploma exam in a table form. It'll more likely to be buried in a page of information in a context. So maybe it's not a question that's, maybe it's the exact same question as this, except it gives you a page of information about you know, the photovoltaic cell that's on the roof of your house, or whatever the case may be, that's generating electricity, generating electrons from sunlight. Okay. But bottom line is, okay, you find that information, it boils down to the exact same question as what we see here. We want to find the maximum speed of the electrons. We say Vmax because we don't know exactly how fast they're moving. We can't predict that. We can only predict the maximum possible kinetic energy, and therefore the maximum possible speed, assuming the energy conversion is 100%. Aluminum surface, the surface is illuminated with 125 nanometer light. This is going to be a wavelength. This is not the threshold wavelength. This doesn't tell us the maximum possible wavelength or any kind of minimum value or anything like that. This is the wavelength, not the minimum or maximum value required to do something. It is the wavelength. Now, somebody take a look at table 14.1 for a second and tell me what I believe it's the work function it gives us. Tell me what the work function for aluminum is from table 14.1. Thank you, Jazzy. So the work function of aluminum is 4.08 electron volts. All right, so we're looking for Vmax. We got lambda. We got the work function. Which of those equations that are on my data sheet or not on my data sheet am I going to use to solve for that question? 1, 2, 3, 4, 5. Counting to 5, because if nobody gives me an answer in 5 seconds, when you're dealing with a photoelectric effect question, if you can't think of which equation to try within about 5 seconds, you're probably going to try this one. Got it? If it's not immediately obvious to you which one you're going to use, then try this one. Hey, listen, just because you can't think of it in 5 seconds doesn't mean for sure that you're going to use this one. But it means you're probably going to use this one. If we're wrong, Okay, if you just couldn't find the right one within the 5 seconds and you try this one and it doesn't work, then that's okay. Just means try another one. But odds are, if you can't get it in 5 seconds or so, then try this one. That's probably the one that's going to work for you. So let's give that a whirl here. Let's say HF is equal to EK max plus the work function. Now, we don't know what the frequency is, but we know that the energy of a photon is not only equal to HF, it's also equal to HC over lambda. So I'm just going to sub in HC over lambda for HF. I also know that kinetic energy of an electron is equal to QV stop, but it's also equal to 1F MV max squared. And the work function we have already. So we sub our numbers in, right? What value of Planck's constant do you want to use here? 6.63 or 4.14? Joule seconds or electron volt seconds? 4.14 because you got work function in electron volts already, right? That seems to be convenient, right? Except that what? Right. As soon as I introduce that equation into the mix, I've got to use joules. No choice. Got to use joules. So let's go 6.63 times 10 to the minus 34 joule seconds times 3 times 10 to the 8. Lambda max was 125 times 10 to the minus 9. And this looks a little ugly because you got a whole bunch of variables in here. And the work function, we have to convert that, right? The work function, 1 electron volt over 1.6 times 10 to the minus 19 joules equals 4.08 electron volts over x joules. We've got to find the x. I get 2.55 times 10 to the 19. Should be 10 to the negative 19, right? Take a look at those questions now, please.